Okay, welcome to the lesson on circular motion. This lesson is supposed to come in term 6. And being the first lesson, it's a trial so that we see how it works out. Then we'll determine which is the best way to help you while we fight this battle with this strange coronavirus. In the meantime, we have circular motion to deal with. And this is different from what you learned in level 1. Most of you may be thinking that circular motion is the same as angular motion. They may have similarities, but they're different. Circular motion refers to the movement of a body along a circular path. In angular motion, you can have a body like a wheel, and then it's spinning about its center. That gives angular motion. So our focus is on circular motion. And let me share the presentation. Let me share my screen so that you can enjoy this presentation. Right, so here in circular motion, we're starting with the definitions. Like I said earlier, the movement of a body along a path which is circular, that gives circular motion. Now, centripetal force, that is the kind of force which acts on this body towards the center of rotation. And of course, this kind of force is also responsible for ensuring that we continue enjoying this circular motion. The reaction to this is the centrifugal force, which acts away from the center towards the outside. And it's given by that expression there, which is mass times the square of the angular velocity times the radius of the path. Let's start with a very simple application of this, which is in a horizontal circle. In a horizontal circle, you have, first of all, 3 forces that could be at play. These include the tension, the centrifugal force, and the weight. The tension, that is for a case where this is anchored at the center. But we are simply saying this is the centrifugal force represented by the letter T, the centripetal force, this is the centrifugal force, and that's your weight. But we are only interested in these 2 because they are the ones we'll be referring to as we proceed with the other calculation there. We'll come back to this later. That's why this statement is saying we're only talking about 2 main forces involved, which are the centrifugal and the centripetal force. And like we said earlier, the tension, or T, which is the centripetal force, is equal to the centrifugal force when you resolve forces in the x-axis. Instead of this m omega squared r, you also have mv squared over r. The other application is for a conical pendulum. In a conical pendulum, you have a member which is being rotated in a horizontal circle in that manner. And you have theta, which is the angle between the vertical axis and the member, this angle here. This is the same as the angle you have there because this line is parallel to that line. So in the end, that's what you see there. So if you look at this, we have, here is our centrifugal force, the weight, then the resolutions, meaning we resolve these ones. How should this make sense? Let me just illustrate it very quickly so you see where these angles are coming from. If you look at your SOHCAHTOA, you have this. Your vertical axis. And then you have another member there, which is representing this member here. So here we are always used to seeing the the angle being formed here. But unfortunately, this time things have changed. We have here the tension, and you have this one, which is the other member. So this T acting like that, that's your T. And then this is your angle, which is the theta. Then if you look at this, this means that you have a right angle triangle right here in the corner. And if you were to resolve, let me just grab this a bit. Okay, great. So if you were to resolve, this is our theta. You notice that this side is opposite the angle. So the ratio between the opposite side and the hypotenuse gives you what we call the sine. So if you were to say sine theta, whether that's your sine theta is equal to the opposite side. That's the opposite side over the hypotenuse. Now, what this means is that if I have to make this opposite the subject of the formula, you will notice that this hypotenuse is actually represented by this T. In other words, we already have our T here. So making opposite the subject of the formula, you will notice we are going to have this opposite will be equal to, whether that's our opposite, it will be equal to T sine theta. That's it. So this is the one we have here as the T sine theta. Meaning that the other one there, if we go by the SOHCAHTOA issues, here we are going to have cos, and it will be adjacent over the hypotenuse, meaning adjacent over T, making adjacent the subject. Here you will have T cos theta. T cos theta. That's it. So you have these two like that. This one, of course, acting upwards, the other one trying to imitate acting in the other direction there. So that's how this should be able to tally in. And as a result, that's how come we have T sine theta here and T cos theta there. Now let's go back to our where we are. We're just here. Great. So we're saying you have T sine theta there, and this is your T cos theta. This is the angle theta right here. So if you start now resolving this, you start with the x-axis. You notice there are just two forces. This one was pointing in the one direction, the other one in the opposite direction. So what you have is just equating these two now, where T sine theta is supposed to be equal to mv squared over r. This gives us our equation 1. So T sine theta is equal to mv squared over r. Then as if that's not enough, we can also do the same for the y-axis. In the y-axis, we have this and this one, where T cos theta, which is this one, is equal to that, meaning summation of upwards forces should be equal to the summation of downwards forces. So that's how come you have your equation number 2 right here. Standing alone like this, they may not make much sense, but we'll make use of them later. For now, we're going to divide equation 1 by equation 2. Equation 1 is T sine theta equals mv squared over r. And this is equation 2, which means we write equation 1 the way it is. And here we are, T sine theta equals mv squared over r. Divide by equation 2. So we divide by, and we pick corresponding sides. So in this case, we have over this one should be here. That's T cos theta equals the right side of the second equation is mg. So that's how come now we have these two arranged like that. Now, if you check carefully, you'll notice that T and T, they are common, so they cancel out. M and M, they're also common, they cancel out. You remain with sine theta over cos theta. By trig identities, we know sine theta over cos theta gives you the next identity, which is tan theta. And as you can see, tan theta is equal to what has remained here, which is v squared over gr. So tan theta equals v squared over gr. That is our expression. From this expression, we can now make v the subject of the formula. If you notice v is carrying a square, you multiply both sides by gr. You have gr tan theta on one side, on the other side you have v squared. So if you make v now strictly the subject, you will need to get a square root for both sides. That's how come we have this now, square root of gr tan theta. Our first example, illustrating what we've just discussed, we have a rope whose length is 5 meters, having a mass of 1.5 kg attached at one end, and rotated in a horizontal circle at a rotational speed of 400 rpm. So what you are required is to determine the tension experienced, forgive that spelling, in the rope. So what have we been given? We have the length. The length of this rope is 5 meters. Rotational speed, meaning rotational speed in revolutions per minute, that's 400 rpm. Angular velocity, we need to convert now this, because this is not the SI unit for angular velocity. So this now requires us to go back there. The formula is 2 pi n over 60. The 2 pi, as we've always emphasized, converts the revolutions into radians. The 60 converts the minutes into seconds, because every minute has 60 seconds. And in this case, we have 2 pi multiplied by 400, then we divide by 60. Now, when you take this into your calculator, your answer will end up being 41888 radians per second. Then our mass is 1.5 kg. Then we also have the, of course, G is standard. We will not need even to bring it up here. Let's go to the solution. In the solution, we'll just resolve in the x-axis. When we're resolving the x-axis, like you might have seen when we're dealing with a horizontal circle, we have T equals that. That's all, because there's just two forces there, this one and that one. So that's how come we have this tension, which is acting towards the center, equals the centrifugal force, which is acting away from the center. So you have T being equal to mass times angular velocity squared times the radius of the path. When you compute these, you should be able to find that answer. You can always verify with your calculators. Let's pick up now something a bit more interesting. This time it's the conical pendulum, which has a rope of length 1 meter and is being rotated in a horizontal circle of radius 60 centimeters. Then you have a mass of 500 grams, which is attached at the end of the rope. So what do we need? We need to determine the angle between the rope and the vertical axis, the tension in the rope, and the speed at which the mass is rotated. So what have we been given? The length of the rope. The radius has also been given. The length of the rope, 1 meter. The radius, 0.6 meters. The mass of the rope, 500 grams. But this should be converted to kgs, meaning you need 1,000 grams to make 1 kg. So when you divide this number by 1,000, what you will have is 0.5 kg. This is the information which we've been provided with. So what are we required to find? We're required to calculate the angle theta, the tension T, and the velocity V. Now, in the first part, I want to illustrate it this way because I think you might have not picked it in the diagram. I want you to take a look at this. You have a rope of this length. Then you have a mass attached at one end. Then you're rotating. Of course, we have the vertical axis coming down there. Then you have the radius right here. So this is your radius. Of course, this is the length of the rope. And that is what we're looking for, the angle theta. So if you look at this angle theta, how can we find it having been given the radius and the length? This is opposite that. So meaning for the lengths alone, let me just remove this so that you don't confuse things. We are now talking about only the length so that we can get the angle clearly. Yes. So what I'm saying is, if you look at this, this is opposite, that's the hypotenuse. So the ratio between these two gives us sine. So we say sine theta is equal to, so we have the radius r over the length l. Forgive my handwriting. Meaning that if you want the angle theta, you have theta being equal to sine inverse. Sine inverse of what? Of this expression we have up here, which is r over l. So that is how come, just considering the lengths, without even talking about the forces, because if we go to the forces, there's something missing, because remember well that we realized that this, in fact, it was tan, this tan theta is equal to, it was V squared over GR. But in this case, if you notice carefully, we do not have V. We're yet to find V. So we cannot use this expression to find theta. That's why we have come to this one to make use of this expression right here. And that's what we are going to make use of. Now let's go back to our, where we are. So sine theta, like we have established, is equal to radius over the length, and meaning that sine inverse of that radius over the length. The radius is 0.6 meters, the length is 1 meter. When you punch this in your calculator, that is what you're going to find, which is 36.87 degrees as your angle. Then T cos theta is equal to mg. Where are we getting this from? This one is simply coming from this resolution we made here. When we resolved in the y-axis, we had this summation of upwards forces being equal to summation of downwards forces. So this is T cos theta being equal to that mg. And that was our equation 2. With that kind of equation, we have this expression here. So if T cos theta is equal to mg, what next? Then it means we can just substitute. Where there is theta, we put 36.87, and m, which is the mass, is 0.5 kg. G, 9.81 by our standard. If you make T the subject of the formula from all this, meaning you multiply that by that to give you 4.905, then you divide by what will come from here. This is what you are going to find. 7.261 newtons. We haven't finished. We still have the velocity to deal with. In the velocity, we have this expression here, which is V equals GR tan theta, which you already arrived at. So G is 9.81, R 0.6, tan theta is, rather theta itself is 36.87, the same one here. Then you have this expression coming out in that way. If you enter this on your calculator, you should be able to find 4.414 meters per second. Again, this is something you can verify and enjoy going through. So that is how you find these expressions. Now, I still have something to show you. I don't know why this one has decided to run away too quickly. Great. Yes, that's better. So after this, we have the last part there, which is the exercise. In the exercise, I've just put a sample, some sample questions. I've just given you 3 of them. The first, second, and the third. If you answer these questions, definitely you should be comfortable with this topic. This topic has 3 other phases because we're supposed to apply these principles on a centrifugal governor, and we should also apply the same principles on forces on a motor vehicle. Then at that point, we'll say we are done with circular motion, and we also got to balancing of rotating masses. So this is the exercise. Remember, this is going to be shared with you, and the same lesson is also on YouTube. The link to the channel will be shared with you. Right. Thank you for now. We've just come to the end of the lesson. And remember, stay safe. We need you back here in one piece. We don't need to lose any of you. Mask up, wash your hands. If you have to go out, ensure that you maintain all those precautions that the health officials are giving us. Keep the distance from others. When you're coughing, use a flexed elbow. Thank you very much. God bless.